Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be looking at some Paper 1 topical questions on the topic of work, energy, and power for Cambridge A-level physics. Now, I've taken these questions from the Papa Cambridge topical questions. I'll leave a link in the description of this video below so that you can download these questions and work with them, especially if you're working topic by topic. But today we're going to work on questions 510 to 525 on the topic of work, energy, and power. And if you just began your A-level journey, then you may have just been introduced to work, energy, and power. But these are concepts that we study throughout our journey in physics. And so the first question is 510 as it's numbered on the Papa Cambridge worksheet. It's from the March 2020 exam. It's question paper 1 variant 2 and it's question 16 from that paper. We are told that a sledge of mass 50 kilograms sits on a snowy surface. It is pulled horizontally for 10 meters against a frictional force of 200 newtons. It is then pulled horizontally across ice for 10 meters and there's no friction between the ice and the sledge. It is then lifted up vertically by a meter and then finally carried back at a constant speed to where it started. And we want to know during which stage of its journey is the most work done on the sledge. So what we could possibly do here is probably calculate the work done for every part of the journey. And so I would start with the first 10 meters when the sled or the sledge is pulled across the snowy surface that has friction. So the first 10 meters, the work done, remember work done is the force being applied to move the object times the distance in the direction of the force that the object moves. So it's pulled horizontally by a force, but the frictional force will also act horizontally. So the work done is the work done against friction to pull the sledge. And so the force is 200 newtons and the distance is in the direction of motion. So cosine theta is 1. So it's 200 times 10, which is 2000 newtons. And so now I need to compare all of the other motions with the 2000 newtons that I have. What about the next 10 meters? Well, the next 10 meters, the sledge is moved across the ice horizontally for 10 meters, but the ice has no friction. So essentially, if the sledge is moving at constant velocity, then no force is required. It will just move at constant velocity since there's no friction across those 10 meters. So the sledge doesn't need any work to be done. So the work done is 0 since there's no friction. What about lifting the sledge? So now I need to pick up the sledge and carry it 1 meter above the ground. The work I'm going to do on the sled is going to be in the direction that I am applying the force, and that's upward, and that's going to equal to the change in gravitational potential energy of the sledge, mgh. It starts on the ground and it goes a height 1 meter into the air. So the gravitational potential energy it gains is the work I put in to get it to that height. It has a mass of 50 kg, so m is 50 times g, which is 9.81 meters per square second, times h, which is 1 meter. And so I get 491 joules. So that's the amount of work I put into the sledge as I raise it a meter into the air. And lastly, we carry the sledge back. How much of work is done there? Well, remember, I'm hoisting the sledge. I'm holding it above the ground. So the force that I'm applying is to give it gravitational potential energy, but I'm walking horizontally back 20 meters. And so the force is upward, the direction is horizontal, those two are perpendicular. They're not in the same direction, so there's no work being done. The cosine of 90 degrees is 0. So I'm not doing any work on the sledge as it's being moved back. Okay, so as you can see from here, the biggest number is 2000 newtons, and that's for the first 10 meters. And so this corresponds with option D. The most amount of work is done when the sledge is being pulled 10 meters across the snow. And so that's option D. You didn't have to write on all the formulae and do the calculations like I did. You could quickly put them into the calculator. But again, you can see that you need to compare every step of the journey if you want to get the correct answer. And so it turns out that the work done against friction was the majority of the work being done. The next question is 511. It comes from the March 2020 exam, question paper 1, variant 2, and it's question 17 from that paper. We're told that an object is moved in a vertical plane from x to y and then from y to z as shown in the diagram. The distances between the various points are indicated on the diagram. Lines x, y, and vz are vertical. The object weighs 20 newtons. How much gravitational potential energy does the object gain by moving from x to z? Well, the object goes from x to y and then y to z, and I want to know the gain in gravitational potential energy. The gain in gravitational potential energy, we'll call it EP, is mg times the gain in height. That's it. That's how we calculate the gravitational potential energy. But they want to know the gain in gravitational potential energy from x to z. So what I want is the change in height from x to z. Well, if I look at going from x to z, what I can see is that the height only increases 3 meters. So the vertical distance from x to z is just that vertical distance. So if I use point x as the reference point, then I've only gained 3 meters in height. And so m times g, which is the weight of the object, is 20 newtons. So that's 20 newtons multiplied by 3 meters. And so this will be a gravitational potential energy gain of 60 joules. And that corresponds to option A. So be careful about this problem. They were giving you extra pieces of information to try and throw you off, but the gravitational potential energy gain relative to a certain point uses the height relative to that point. And that's why we use 3 meters rather than 6 meters. They were trying to throw you off with these different values. Vertical height, not diagonal height, so you would use 3 meters. Okay. The next question is 512. It comes from the summer 2020 exam. So summer being May, June 2020, question paper 1, variant 1, and it's question 17 from that paper. We're told that a block of weight 80 newtons is pushed a distance of 60 centimeters up a slope inclined at 30 degrees to the horizontal. There's a frictional force of 25 newtons between the block and the surface of the slope. We want to know the work done, Wg, against the gravitational force, and the work done, Wf, against the frictional force. So the two different types of work that are being done here. So the first thing I'm going to do is trying to figure out how much of work am I doing against gravity. And that's going to be the change in gravitational potential energy. So what I need to know is the vertical height difference that the block will be moving when it goes up the slope. So what I will do is just draw myself a right angle triangle. Okay, and these different heights as the block moves up the inclined plane. But it moves a distance of 60 centimeters. The vertical height that it changes when it moves 60 up the slope is h, we'll call it h, and this angle is 30 degrees. So with a little bit of geometry, I can see that sine of 30 degrees is equal to h over 60, which means the vertical height change for the block is 30 centimeters, which is 0.3 meters for my calculations. So the work done against gravity is the gain in gravitational potential energy, mgh, which is the weight of the block, m times g, which is 80, times its gain in height, 0.3 meters. And so this is 24 joules. So it gains a gravitational potential energy of 24 joules. That's the work done against gravity. That's the work done raising the object vertically. But raising it up the slope, Wf, is the work done against friction. So it's the frictional force, the amount of force exerted on the object by friction times the distance over which that friction acts. We'll call it d. And this is 25 newtons times a distance. Now this distance is different. It's 0.6 meters. It's 60 centimeters because the friction acts over a distance of 60 centimeters. And this gives us 15 joules. So this corresponds with option B. 24 joules against gravity, 15 joules against friction. So just be careful about using the same distance for the work done against gravity and the work done against friction. they're moving in different directions, and so the distances they move against each force is different, and so the work done will depend on a different distance and hence be a different value. 24 and 15. Now, question 513 is from summer 2020. It's from question paper 1, variant 1, and it's question 19 from that paper. It says that power is transferred through a machine as shown. We have some input power going into the machine and then some output power, and then there's some power lost as well. And we want to know the efficiency of this machine in terms of PI, PO, and PL. Now, we always, to reduce confusion, should write the equation for efficiency down as we remember it. What is efficiency? Efficiency is the useful output power that we get from a device divided by the total amount of energy going in. The closer this value is to 1, the more useful output we get from the device and the more efficient it is. So the useful output is PO. The power output is PO, and the total input is PI. So maybe they were trying to throw you off with the power loss, but remember, the greater the power loss, the smaller this ratio. And the smaller the power loss, the greater this ratio. And so the efficiency is simply PO over PI, and it's not equal to 1. Shouldn't be equal to 1 because there's power loss. And so this corresponds with option D. So again, you remember your definitions, remember your theory, and don't let anything sort of deter you from remembering the theory in the correct way. What is efficiency? Useful output over total input, irrespective if there's power loss, etc. That will determine what the efficiency is, but the ratio will still be output over input. Okay, and that's how we calculate efficiency. Now, there's a few questions on efficiency, and 514 is another one like that. We are told that during an interval of time, fuel supplies energy X to a car. Some of this energy is converted into kinetic as the car accelerates. The rest of the energy Y is lost as thermal energy. What is the efficiency of the car? So the first thing I would do is I would find what my total output is, or rather total input, and then useful output, and then find the ratio that I need to. So the total input of energy is X, because that's the amount of energy supplied by the fuel, the chemical potential energy. And the useful output is that which allows the car to accelerate, that which is converted to kinetic energy. The total energy minus what has been lost as thermal energy, X minus Y. And so therefore, if I want to find the efficiency, so efficiency is, again, useful output. If you remember this one equation, you shouldn't really make a mistake with any of these efficiency problems. Almost certainly guaranteeing you getting this correct. So efficiency will be X minus Y over X. And this corresponds to option C, X minus Y over X. Always make sure you check your answers. My suggestion would be to circle the answer that you think the most correct on the question paper before shading the correct answer in the answer sheet, just to make sure you double check if you do have time at the end of the exam. The next question is 515. It's from summer 2020, question paper 1, variant 2, and it's question 15 from the paper. Now they ask us here, and in which situation is work done on an object? An object slides with constant velocity along a frictionless surface in a vacuum. The person holds the object at arm's length at a fixed height above the ground. The person pushes the object up a frictionless ramp. The stationary object floats partially submerged in water. So I think if we try to remind ourselves what work is done when a force moves an object. Specifically, when a force moves an object in the direction of the force, but we just need a force moving an object. That's the fundamental idea behind work. So immediately I can start to eliminate some of my answers where objects are not moving or force is not being applied. When an object moves at constant velocity across a frictional surface, there isn't any force required, so no work is done. When an object is held at arm's length at a fixed height, it's not moving, so no work is done. When a person pushes the object up a frictionless ramp, it requires a force because it must oppose gravity. So that's possible case of work being done. And lastly, the stationary object floating submerged in water, that's an object not moving. So by process of elimination, you can see that the answer is C. And I'll just draw a quick simple diagram to show you, well, here I have my object, and the object, it is at some height h1 above the ground. We apply a force F to oppose its parallel component of weight, or its component of weight parallel to the slope. It then has a final position higher up the inclined plane, and at this inclined plane, its center of mass is a distance h2 above the ground, and the work that the person does to take it up the ramp is the change in gravitational potential energy, since there's no friction, and this is mg delta h. So yes, work is done when a person pushes an object up a frictionless ramp, because even though it's frictionless, it's going up a slope, and so its gravitational potential energy is changing. Work must be done against the component of weight that is parallel to the plane. Okay, so that's question 515. The next one is 516 from summer 2020, question paper 1, variant 3, question 17 from that paper. Now, this may look like a thermodynamics problem, and it probably wouldn't come in AS physics, but you don't really require knowledge of thermodynamics to be able to answer this. So you could get a question like this in the exam. Even though thermal physics has been moved to A-level physics to year 2, it might be a good idea to prepare yourself for this kind of question. And I'll show you why. A cylinder is heated, causing the air inside to expand at a constant pressure of 2.2 times 10 to the 5 pascals. And the piston is raised 0.5 meters. The expansion of air causes the piston to rise through a vertical distance of 0.5 meters. And 11 kilojoules of work is done in the process, with frictional forces being negligible. And we want to find the cross-sectional area of the piston. Okay, so the pressure remains constant, but the piston moves, meaning the gas is expanded. And we want to know how much work is done on the piston. Or rather, to give us the work done on the piston, they want to know the cross-sectional area. So from your understanding of your concepts on, well, work and pressure, what you do know is that pressure is the force per unit area. So you do know that what pressure is. That means the force applied on the piston is the pressure times the area. But wait a minute, the work done on the piston is the force times the distance in the direction that the force is applied. Force is applied upward, the piston moves upward. So it's the same force I've been talking about. It's the pressure times the area times that distance. These are all things that we know. So the area is the work done divided by the pressure times the distance. And I have these values. It's 11 kilojoules of work, which is 11,000 joules, divided by the pressure, which is constant, 2.2 times 10 to the power 5, multiplied by the distance, 0.5 meters, 50 centimeters. And so we get a cross-sectional area of 0.1, which is 1 times 10 to the minus 1 square meters. And this corresponds with option D. So do you need to know your thermodynamics? It's clear that we don't need it. We can actually derive the equation that we require that relates work to pressure and cross-sectional area. I'm not sure if this would be a kind of question, but it's something that you know the definitions of pressure and area and so on. So it is possible. And that's 516. So just be very careful that you are prepared for a question like that. 517 is electric fields. That has definitely moved on to A-level physics, so that will not be in an AS physics paper, not be in paper 1 or paper 2. but it was in the past. Hence, it's in this collection of questions. And the next question is 518 from summer 2019, question paper 1, variant 1, and it's question 17 from that paper. We're told that a rope is attached to a sledge and a boy uses the rope to pull the sledge along a horizontal surface with a constant velocity. The tension in the rope is 100 newtons and the rope is held at 30 degrees to the horizontal. We want to know how much work the boy does on the sledge when he pulls at a distance of 5 meters along the surface. Okay. So what happens is we have a sledge here that's being pulled at constant velocity. The force is acting 30 degrees to the horizontal, and that force is 100 newtons. And it's moving at constant velocity, so the horizontal component of the force that is being applied by the boy is opposed by an equal and opposite frictional force, which we'll call little f. And basically the work being done is the work that's done to oppose the friction. And this frictional force is the horizontal component of the applied force, since it's moving at constant velocity. That's 100 cosine 30 degrees. And this is 86.6 newtons. And so this horizontal component, if we call that applied force uppercase F, then this is uppercase F subscript X. That's the force being applied on the sledge to move at constant velocity. And so the work done, W, is F times X in the same direction. That's 86.6 in the horizontal direction times a distance of 5 meters in the horizontal direction, which gives us a total work of 430 joules. And so that corresponds with option C. So the work done, remember, is that to overcome the friction. And so you need to find the frictional force multiplied by the distance over which this object is moved through the friction. As long as the two are in the same direction, you can multiply them and you can get the work done. The next question is 519. It's from summer 2019 exam. Question paper 1, variant 2, and it's question 17 from that paper. We're told that a combined heat and power station, a CHP station, generates electrical power and useful heat, and the diagram shows the input and output powers for a CHP station. We get some input power from fuel. 60 megawatts is wasted, 160 megawatts is used for useful heating, and 100 megawatts is used for useful electricity. And we want to know what the efficiency of the CHP station is for producing useful power. Efficiency should always be what's useful divided by everything that comes in general. So basically, we want to know how efficient is the CHP station at the C and at the H and at the P, the heat and the electrical power. So we basically want to know how effective is it, or how efficient it is, producing heat and electrical power, not just electrical power. And so efficiency is always useful output. Now, we don't always want heat energy, but in this case we do want heat energy because the power station produces heat energy as a useful byproduct. And so useful output over total input would be 160 useful megawatts for heating plus 100 useful megawatts for electrical power. And the total output is basically everything that went in must be everything that comes out. It's 160 plus 100 plus 60. And so the efficiency is 0.81, which is 81%. Remember, this is a very high efficiency, but we are including heating in this efficiency. You see, if we remove the heating, then the efficiency would drop. But then that wouldn't be a CHP station. It would just be an electrical power station. And so this would correspond with option D, 81%. So always remember, efficiency is useful output over total input. Next is question 520. It's from winter 2019, that's October-November 2019, question paper 1, variant 1, and question 15 from that paper. Again, another question about efficiency. We're told that an electric motor produces 120 watts of useful mechanical output power and the efficiency of the motor is 60%. Which of these rows are correct? They ask us to find the electrical power input and the waste heat power output. Okay, so we need to calculate two things, but let's just go back to our equation for efficiency, because that's always going to save us. Efficiency is useful output. Again, obviously you're not going to write this equation down every time. If you remember it, that's great. You just need a calculator. Useful output over total input is efficiency. And so 0.6, the efficiency, 60%, is the useful output, 120 watts, divided by the total input, which I want to find. So the total input, if I rearrange this equation, is not difficult to find. Must be higher than 120. Total input will be 200 watts. So 120 divided by 0.6. So that already eliminates A and B. I'm left with options C and D. But I need to find the waste. Now the waste is the useless power, the heat that's produced. And that's going to be the total input minus the useful output. What isn't useful will be waste, and that's equal to 80 watts. And so 200 watts of total input is matched by 80 watts of waste output, so that corresponds with option D. So just remember your formulae for efficiency, and the process will always be common. There shouldn't be that many questions, but it's always good to remember the simple formula when solving these problems. Question 521 is very specifically based on thermodynamics, thermal physics, which again is A-level physics, so I've ignored that question, and then I moved on to question 522, which is similar to one we've solved already. And this is from the winter 2019 exam, question paper 1, variant 2, and question 14 from this paper. We're told that a gas in an engine does work on a piston of cross-sectional area 80 square centimeters. The pressure on the piston has a constant value of 4.6 times 10 to the 5 pascals. And we want to know how much work is done by the gas on the piston when it moves through a distance of 25 centimeters. Okay, so again, the piston is moving in a certain direction. The force is applied in the direction of motion. And the pressure is the force per unit area by definition, meaning the force applied on the piston is the pressure times the area. The work done by definition is force times distance in the direction of the force. And so the work done is the pressure times the area times the distance, because I already have an expression for F. So the work done is PAX. The pressure is given. It's a constant 4.6 times 10 to the power 5 pascals times the area. It's 80 square centimeters, so that's 80 times 10 to the minus 4 square meters multiplied by 0.25 meters. How did I get this? Well, what I know is that 1 centimeter is 10 to the minus 2 meters, correct? So if I wanted 1 square centimeter, that is squaring everything on the left-hand side, I must square everything on the right-hand side. So 1 square centimeter would be 10 to the minus 4 square meters. Always make sure you get your units correct when doing conversions, because there will be common mistakes added as solutions, as options, as part of the solutions list. So having done the correct conversion, I should find the work done to be 9.2 times 10 to the power 2 joules, 920 joules. And this corresponds with option A, 920 joules, 9.2 times 10 to the power 2 joules. Again, you can look at the other numbers and see that they're actually quite large. For a very small piston, you shouldn't be expecting that much work to be done. 92,000 joules would be a bit much to move that piston. So you could, by process of elimination, eliminate B, C, and D, and orders of magnitude choose option A, but it always will be good to do the calculation just to make sure that you are choosing the correct answer. Question 523 is from the winter 2019 exam, question paper 1, variant 2, and it's question 16 from the paper. We're told that a wooden cylinder floats partially submerged in a bath of water. A force F is applied to the cylinder until it is just fully submerged. And we want to know which statement is not correct, meaning 3 are correct and 1 is incorrect. So what's happening to the cylinder? Let's draw a free body diagram. It's being submerged and there's an upthrust of U pointing upward and a force F that's being applied to pull it downward. And there's also its weight acting downward, W. And we want to know which of the statements are not correct. So let's test, well, each one of these. Some of the water gains gravitational potential energy. Well, what happens when we move an object, or submerge an object underwater? The water level changes. The object will displace its volume in water. That amount of water will be displaced when the object is submerged. So that means that the water level rises slightly. If the water level rises, then some of the water will gain gravitational potential energy. So the first statement is true. What about the second statement? The cylinder loses gravitational potential energy. Will it? Yes. Well, it falls. Its height is now lower relative to the bottom of the tub of water. So the cylinder falls relative to the bottom of the cylinder, to the tub of water, and so it will lose, the cylinder loses gravitational potential energy. So yes, the second statement is correct as well. B is correct. What about the work being done? Work is done by the force F on the cylinder. Well, the force is downward and the cylinder moves downward. So the force is downward, the motion is downward. What does this mean? That means the W, the work is done by the force F on the cylinder. So work is done by the force because the force and the motion are in the same direction. And the last statement says work is done by the upthrust on the cylinder. Now the upthrust is acting upwards, but the motion of the cylinder is downward. And so what this means is work is not being done by the upthrust, but work is being done on the upthrust. Remember, by definition, it's in the opposite direction to the force, so work is being done on the force. And so that's the incorrect statement. Work is not being done by the upthrust, work is being done on the upthrust. And so that's option D. So we tested each one of these statements and we found the one that is not correct is the last one. Work is done on a force when the force is opposite to the direction of motion, 180 degrees difference. Next is question 524. It's from the winter 2019 exam, question paper 1, variant 3, and it's question 15 from that paper. We're told that a piston in a gas supply pump has an area of 500 square centimeters and moves a distance of 30 centimeters. The pump moves the gas against a fixed pressure of 4,000 pascals, and we want to know the work being done by the piston. So again, we've done similar questions like this. The pressure in the piston is the force being applied against the piston over the area of the piston, meaning that the force is the pressure times the area. The work being done by definition is force times distance in the same direction. And so this is pressure times area times x, which we know the pressure is 4,000 pascals. The cross-sectional area is 500 square centimeters, so we multiply that by 10 to the minus 4 to get square meters. And we multiply that by a distance of 0.3 meters. So I've just converted everything to SI units, so we get an answer in joules. And we should get an answer of 60 joules. So again, when you have a question like this, always remember the definition for pressure and the definition for work. Put them together and you get an equation for work in terms of pressure and area. And so this corresponds with option A. Now, the last question we'll do for this video is 525. It's from the winter 2019 exam, question paper 1, variant 3, and it's question 18 from the paper. We're told that initially 4 identical uniform blocks, each of mass m and thickness h, are spread in a table. The acceleration of free fall is g, and we want to know how much of work is done on the blocks in stacking them one on top of the other. If I want to know how much of work is done in a situation like this, what I know is that the thing changing for these blocks is the total gravitational potential energy that they have. So what I would do is calculate the initial potential energy for the 4 blocks lying side by side, and then the final potential energy for the 4 blocks stacked on top of each other, and then subtract the 2 potential energies. And the difference in potential energy will be the work that's done, because the work must be the one supplying the energy for them to change the gravitational potential energy. So what's the initial potential energy? Well, the initial potential energy is 4 times, they all have the same mass, they're all identical. So I'll call them mass m, since they're all identical, and times mg. Now, what's the height of each block? I can't say h because all of their heights, none of their mass is not located at the top of the block. Neither is all of the mass located at the bottom of the block. So if I consider the center of mass, the height of the block will be h over 2, half the vertical height of this block, thickness of this block. And this is me considering centers of mass for each of the blocks. So the total gravitational potential energy is 4 times a half mgh, which is 2 mgh. So the initial potential energy is 2 mgh if I consider that all of the masses are located at the center of each block. So it's mgh over 2 plus mgh over 2 plus mgh over 2 plus mgh over 2, which is 2 mgh. Now, finally, the potential energy is, when all the blocks are stacked on top of each other, is 4 times the mass. There's 4 blocks, and the center of mass of these 4 blocks is at a height of 2h. Initially, I'll just draw a tiny little arrow. The height was a half h. So the center of mass of the 4 blocks put together, if they were one complete system, was 2h. So that's 4 times the mass times g multiplied by 2h, which is 8 mgh. Aha, so now I have different final potential energy as I do to the initial. So they have different potential energies before and after. So the work done in stacking the blocks is the change in gravitational potential energy, which is 8 mgh final minus initial 2 mgh, and the work done will therefore be 6 mgh, and that corresponds to option B. So always be careful when you see a question where they ask you to find the gravitational potential energy of a tub of water or a block. They're more than likely going to say, hey, it's a tub of water, meaning its density is uniform throughout. Or it's a uniform block, meaning its mass is uniform throughout. And so using that idea, you will always assume that the height above the ground level, the reference level, is always the central point, the center of mass in this case, because the object should have a nice regular shape. And so that's how we calculate work done. It's a change in gravitational potential energy, in this case 6 mgh. So a little bit of a tricky question. I hope these questions were helpful. If they were, please leave a like, leave a comment, subscribe to the channel if you haven't already. But from me, Mr. K, that's all for now. I'll see you again next time on Everything is Relative.